So thank you again for the opportunity to talk to you about our program and the work that led up to it. So yeah, here we go. I'll start with some disclosures before I go into detail. I'm an inventor of a number of patents related to the technologies that will be presented and the executive director of a company that received funds from the IP. I've acted as a clinical trials consultant for various companies as well. And here's a list of different funding bodies that supported our work. So before going into our program, I'll give you a brief overview what it is part of in Australia. EpiGenes is one of the 5 programs or projects forming the Genomic Screening Consortium of Australian Newborn, or GeneScan. There are 2 programs that use genomics as a first year, whole genome sequencing. One program that evaluates health economics in the landscape across the programs, and 2 programs, including ours, using genomics as a second-tier test. So I'll be talking to you about our program specifically. The GeneScan Consortium was awarded $50 million from Australian government's Genomics Health and Future Mission, GHFM, last year for 5 years. GeneScan's aim is to explore feasibility, effectiveness, health economic, ethical, and equity aspects of applying genomics in newborn screening. And it's not just restricted to genomics, it's really omics, epigenomics, metabolomics, ethics, equity, economics, anything with omics, apart from stakeholder engagement. So if you want to know more, here's a QR code. Please log in and have a look. And email the relevant people if you want to follow up for any of the projects, including mine. So now to the program, our program, EpiGenes. What is the main problem that we are trying to address? The main problem is that, as you're aware, there are over 7,000 rare diseases with delayed diagnosis, on average 4 years of age. During this time, families consult on average 5 doctors and receive 3 misdiagnoses. This has significant negative consequences for health and economic outcomes for them, their families, and our health system, our health systems. Genomic newborn screening for rare diseases offers the promise of earlier access to new therapies to transform development and health trajectories. One limitation, however, is availability of accurate, cost-effective genomic workflow, which are in line with current newborn screening program requirements. So the critical gaps are that state-sponsored newborn screening programs are unprepared for many conditions to be identified by first-tier genomic newborn screening. Critical gaps are in knowledge, which are lack of low-cost, accurate, screenable tests informed by optimized population scale, meaningful cut points, and knowledge of natural history for various rare diseases screened at population level, not from necessarily biased ascertainment. This includes mild and some subclinical cases less likely to experience the benefits of screening, but equally exposed to its harms. The whole thing is a balance between harms versus benefits. So we need evidence that benefits would likely outweigh the harms, including costs. Our solution is EpiGenes, epigenomic newborn screening workflow to meet current newborn screening requirements. It employs first-tier DNA methylation screen on a single 3mm newborn blood spot punch, and this is followed by second-tier genomic testing on another punch for the NBS, which are positive for the suspected conditions. So genomics is only done on a small number of samples with abnormal methylation signatures, not on all the samples. And there are roughly more than 120 rare diseases that fall into this category. This includes imprinting disorders, X-linked disorders, which can be targeted by our workflow. For these conditions, changes in DNA sequence cause changes to DNA methylation and can be used for screening and diagnostic testing purposes. And you can read a couple of reviews, one's from us, and there's one from Canada, listing a number of these conditions with abnormal methylation signatures, but also abnormal genomic CNV results of SNPs. In its current iteration, Epigenes screens for treatable conditions associated with intellectual disability, autism, life-threatening obesity, and seizures, including Fragile X, Prader-Willi syndrome, Angelman syndrome. Angelman has gene therapy, ASO clinical trials currently underway, which is quite exciting. And G15Q, Turner syndrome, and various sex chromosome aneuploidies. Most infants with these conditions do not receive diagnosis in the first year of life, other than Prader-Willi. Work is underway to increase the number of conditions screened in this panel at little additional cost. So we are currently looking at expanding this panel considerably. For the first tier screen, we have developed MSQMA, methylation-specific quantitative melt analysis, as a low-cost, effective quantitative DNA methylation-based screening test. These are a couple of initial papers that looked at this in Fragile X and then expanded to other loci. If you're interested, please go have a look. It's got more technical details that I will cover today as part of the presentation. We've used and tested with this number of different types of samples, including fresh and archival newborn blood spots, showed high PPV, positive predictive value, negative predictive value, sensitivity, and specificity in different settings. To date, we have 21 publications that used MSQMA from over 25,000 neurotypical individuals, most of them newborns, and over 700 individuals affected with different rare diseases, including 75 with Prader-Willi, 80 with Angelman's, over 500 with Fragile X, and over 100 with different sex chromosome aneuploidies. So it's quite solid, at least for the ones that in our current panel in terms of reference ranges that we've established. And these are a couple of papers that sort of detail some of this work. So what is MSQMA and what are its strengths compared to other methods? MSQMA combines the quantitative strengths of high resolution MELT with high throughput quantitative real-time PCR analysis. So we're actually getting DNA concentration after bisulfite conversion. So we know how much DNA there is, and combining that information with high resolution MELT information that we're getting in the single closed tube format, which is different from qualitative analysis of just methylation profiles or high resolution MELT. It uses only one 3 millimeter NBS punch in a single sample with a failure rate less than 2%, which is in line with requirements with testing for standard of care newborn screening. It can be used to analyze any locus with a differentially methylated regions with up to 20 loci targeted per single punch or bisulfite conversion. Cost is analogous to what is currently what the current cost is for SCID and SMA as part of standard of care newborn screening. It uses very similar equipment as well. So what does it do? It provides accurate automated quantification of DNA methylation in a single assay, including analysis of DNA concentration of target amplicons, not DNA concentration of the whole of everything, but of a specific amplicon that you're targeting and looking at methylation of, which may be different to the global DNA concentration and quality. And also provides high resolution MELT profiles post bisulfite conversion. It provides analysis and flagging of data that does not meet quality control requirements, very key for poor quality and low quantity fragmented DNA, like newborn blood spots, and provides automated recalculation of methylation ratio once data that does not meet QC parameters has been automatically discarded based on the filters in the software. We've also used it to demonstrate prognostic utility on newborn blood spots, and I'll show you some data on this. So analysis of MSQMA raw data is performed by custom designed user-friendly web-based software called QMax. QMax simultaneously performs all steps and QC steps and analysis steps. It doesn't matter how many samples you go through, it's independent of the quantity or the number of samples that are uploaded. It's very quick. It has been tested in different labs with different real-time PCR machines used for SCID and SMA testing and standard of care newborn screening. This is what it looks like. On the left, you've got aligned fluorescence, so you upload your HRM raw data, and the software spits out optimal temperature, or analyzes them at an optimal temperature for this assay, and then you also upload your real-time PCR data from post-by-software conversion. It's useful to calculate quality control and DNA concentration. And then you've got on the top the name of the assay, and then it all is combined with different filters just before the equal signs, and then it spits out a file which gives you DNA, the methylation ratio for your applicant, and DNA concentration post-by-software conversion, and any flags for any of the samples that did not pass QC. So that was the first year test, but what is the workflow? The workflow is we punch the blood spots, a single punch in 96 well plates, one per plate, which are barcoded. This goes through our process, largely automated, and then it goes transferred into 384 well plate into a real-time PCR machine for MSQMA analysis. Largely, we've been targeting imprinting and X-linked loci with this approach. Then we get positive signatures, epigenetic signatures, and expected methylation ranges for the conditions that we're screening for. I'll show you some examples in follow-up slides. And then that goes, those shortlisted samples. So let's say we've done 100,000. Out of that, would have 500 to 800 that are positively abnormally methylated for loci that we're looking for, and only those 800 go for second-tier punching. Again, 96 well plates, single punch per well, and that goes, depending on the signature, it goes for a combination of second-tier tests, which are droplet digital PCR and epitope-based methylation analysis, which is more expensive than our first tier, but it's quite quantitative as well. So we're using that to confirm methylation signatures, digital PCR CNV analysis, where we've got abnormal copy number suspected at the locus, let's say that's associated with Angelman Prader-Willi. And for Fragile X, which is trinucleotide expansion disorder, we use AmplideX PCR to confirm abnormal methylation signatures are due to expansion with the FMR1 gene. And also low coverage whole genome sequencing that tells you if we get a signature on the chromosome 15 on X chromosome, where exactly the copy number changes are that cause this abnormal epigenetic signature. So taken together, irrespective of what the positive predictive value is for the first year test for a condition screen, altogether, a positive hit on the first plate and a second plate results in PPV from both punches approaching 100%. So it's almost 100, almost diagnostic. But if it were in newborn screening settings, you would need to collect saliva sample anyway, because there is a chance of blood spot being mixed up from the wrong infant. But using the data from both first and second tier screen provides quite a bit of certainty that you will not be bothering many families that should not be bothered, that are not affected with the conditions that you're screening for. So sensitivity and specificity for full mutation alleles for Fragile X approaches 100% in both sexes on a single 3mm punch, and I'll show you some validation data here. It's been published. And so what I've got here, before I go through these panels, I've got this key. It sort of describes what's being presented. So field dots are non-mosaic individuals. Each dot is a separate individual. Open dots are mosaic individuals confirmed by standard of care diagnostic testing. CN on x-axis for both axes is neurotypical controls. M is male, F is female. PM is premutation FMR1 expansion that does not cause Fragile X, but is associated with late onset conditions. We are of an overview that is probably, for this purpose, it's not appropriate to pick it up as part of newborn screening because it causes all sorts of ethical issues. And there are a lot of them, a lot more than full mutation that cause Fragile X. So here you can see on the left results of MSQMA on the y-axis, and you've got different groups on the x-axis. And you can see that the normal male range for 89 individuals is roughly less than 0.03. For females, because this is exon activation sensitive, the methylation ratio is between 0.2 and 0.4. And then you've got male and female pre-mutations that are very similar to controls. So largely you cannot differentiate using this locus pre-mutation from controls. So you don't pick up pre-mutation and don't have to face those late onset related issues. But you are picking up the vast majority of full mutations that cause Fragile X in males and females. And on the right, you've got the second tier methylation epitype test that we use, and it gives you very similar results. So, which is great. So we have a way of confirming methylation in that locus, which is not only relevant to Fragile X, but also other X-linked conditions that cause skewed X activation. And it also has prognostic utility. This is a study we've also published where we've analyzed methylation using MSQMA of FMR1 of newborn blood spots retrospectively retrieved from a cohort of individuals affected with Fragile X, males, 2 to 17 years of age. We've done deep phenotype analysis assessments in these individuals. So we've done formal intellectual functioning assessments, behavioral issues. ADOS2 is one of the gold standards. And so here we've got a relationship of methylation at birth and the phenotype severity from 2 to 17 years of age. And you can see that there's a very, very strong correlation between methylation at birth and what happens later on in males, irrespective of whether you're mosaic or non-mosaic, and behavioral features as well. So that's great, I think. Now to validation for chromosome 15 imprinting disorders, so Angelman's, Prader-Willi, and G15Q. These conditions are caused by deletions, duplications, or epimutations to the same region, 15q, 11q, 13. It contains a SNRP and SNRPN gene promoter, which is differentially methylated, so depending on parent of origin. So maternal alleles are methylated, paternal alleles are unmethylated. In neurotypical individuals, you get one from mother and one from father, so methylation is around 50%, close to. However, if you got Angelman syndrome or Prader-Willi syndrome, there's deviations. So in typical Angelman's, it approaches 0. All the methylated alleles are coming primarily from the father, and for typical Prader-Willi, all the methylated alleles are coming from mother. You do get G15Q with multiple copies of either maternal or paternal region, of this imprinted region, or Angelman's and Prader-Willi mosaic individuals, and these individuals have deviations from 50%. So they're between normal range and typical Prader-Willi and Angelman's range. And this is why it's important to have quantitative analysis if you want to pick this up. So what do I have here? This is from a recent JAMA paper, JAMA Network Cochrane paper that we've published. On the right, you've got a diagnostic sample. So you've got 39 blood from 39 individuals affected with Angelman syndrome. All of them are giving us methylation below 0.02 for typical Angelman's. So we're going from right to left. Then you've got maternal G15Q. The range is roughly between 0.7 and 0.85. Then you've got mosaic Prader-Willi, which is around 0.9, and then you've got typical Prader-Willi, and there's about 60 more than 60 individuals there, and most of them are giving us results between 0.99 and 1, which is what you'd expect. And the good quality samples, blood samples, are giving us a range around 50, from roughly 50 to 60. I know with this percent methylation ratio, 0.5 to 0.6 methylation ratio. On the left of this graph, we have newborn blood spots. There's around 1,300 of those. And then we've got mixed in typical Prader-Willi blood spots and Angelman's blood spots. So the sensitivity and specificity was approaching 100%, but the quality of these materials is not as good as the quantity as what is on the right. Long story short, we've picked up all of them correctly, other than Angelman's caused by UBE3A mutations, and we would not expect to pick them up because they are not abnormally methylated. So this is a limitation of this assay. We're not picking up Angelman's due to UBE3A mutation with the current setup. There was one sample that had poor quality, the yellow one that was an outlier in the control population. I've got two types of bisulfite conversions here, one using Zymo, the other one QIAGEN. They gave analogous results and reference ranges. So now that we've validated this, the first part was to look at this at population scale. So we've applied it to 6,600 roughly newborns, consented for de-identified research, providing materials through Victorian Clinical Genetic Services, so our pathology organization. You can have a look at this paper. There's a QR code here for further details. This is probably the main figure in that paper. So this is actually showing the results from the first year screen. And what you can see here, these samples are not as good as what you get from prospective punching. These are archival samples, more than 6 years of storage at room temperature. But nevertheless, we could perform analysis on them. And so you've got here methylation on the x-axis and the allele frequency, or not frequency, on the y-axis. So how many individuals had that specific methylation? And you can see the vast majority fall between 0.25 and 0.77 MR. The suspected Angelman's outliers on the left are between 0.05 and 0.12, and for Prader-Willi it's roughly 0.9 to 0.97. And so suspected Ju15Q that were shortlisted for second tier testing around 0.8. So this one was typical Angelman's. On another plate, we've confirmed it had type 2 deletion by low coverage whole genome sequencing and droplet digital PCR. This one was typical Prader-Willi. So abnormal methylation, but normal copy number changes. But but methylation was confirmed to be abnormal by multiple methods. This was mosaic Angelman's confirmed by ddPCR. This was mosaic Prader-Willi. And this was a typical Ju15Q isodicentric confirmed by both digital PCR and low coverage whole genome sequencing on another punch. This is what our genomics data looks like, low coverage whole genome sequencing data looks like on another punch. We modified the method that is currently used for non-invasive prenatal testing to work on blood spots. On the x-axis, you're seeing the whole chromosome 15. On the y-axis, you're seeing the copy numbers in the bins. This is shotgun sequencing. This is called shotgun sequencing. And so the blue line shows the number of dots that are associated with 3 copies, and the other below shows 1 copy. And you can see that for the suspected Angelman's with methylation less than 0.05, you're getting a single copy within the classical 15q imprinted region. For the Ju15Q that was shortlisted, we're getting a signal for a portion of that region that has 4 copies and a portion that has 3 copies. This is the typical picture that we see for isodicentric, maternal isodicentric individuals that run through the same assay. And when you zoom in on the genes that are affected, this is what you'd anticipate to get for typical Angelman's and typical Ju15Q. So type 2 deletion for Angelman's, and for isodicentric, getting these larger regions, and the importantly, all the breakpoints matched what was expected. So outcomes of this study were prevalence for Prader-Willi and Angelman's was considerably higher than previous estimates from biased statement. Maybe we got lucky with Angelman's and Prader-Willi and pick up twice as many as we would expect. But there might be a few reasons for it, which I'll discuss in follow-up slides. For Ju15Q, however, we got what we anticipated, roughly 1 in 12,000. The methylation thresholds, and I guess the previous webinar that was run by RTI, there was a question asked, what is the clinically meaningful methylation threshold in regards to mosaicism? We think that less than 0.25, or 25%, is clinically meaningful for Angelman's at least. And we know this because we've analyzed mosaic individuals with Angelman's from biased and this is a publication you might want to have a look at. These individuals do not present with your typical Angelman's. They have verbal, they're a lot higher functioning, but nevertheless they're quite affected. So in a different way, but still Angelman's. So we think it's still worthwhile clinically to identify these individuals. And so, but to really know what is meaningful in real life settings, you need to run a population study. And so this is what we got our funding to do. So last year we received 3 million from Australian government for a 5-year program to explore that very aspect. And this is linked to a 55 million whole of state natural history study called GenV. There's a link there, and below I've got a link with details regarding how our program is linked to GenV. What is GenV? GenV has recruited over 2 years over 100,000 individuals from our whole state and linked all of their records and through our pathology company, BCGS. And so what it has been doing has been not only collecting biospecimens, but also collecting data. And there are planned waves that the data has been already collected at birth, and there's wave at 1 year, 2 years, and 3 years. And so what we are planning to do, and what we are doing, is in the first 2 years of the project, we are performing screening of over 100,000 using this workflow for the panel of conditions. Then in the last 2 years, we're doing confirmatory testing on another punch. We expect to identify 200 individuals affected with the conditions we're screening for, and then we'll plan to do case cohort comparison. So we'll be comparing the trajectories of individuals with a condition screen against the whole cohort. And then through this, we will be defining clinically meaningful thresholds to see whether for instance, to see whether 25% is clinically meaningful for Angelman's, or whether it should go down or up. This will provide accurate prevalence estimates. So if we got twice as many in 17,000, we'll see whether this holds in 100,000. The numbers will give us a lot stronger confidence to say what the prevalence is with this particular workflow. And we're also planning to compare cost effectiveness of this approach at scale versus standard care diagnostic testing. We'll be able to link to diagnostic results, the data that we collect from newborn screening. And then we plan to apply it, like in US where you've got RASP, there is a system in Australia as well. We plan to collect all of this evidence and apply for addition of this panel to standard care newborn screening. And hopefully Angelman's will have a ASO up and running by then. So the program, we targeted, or GenV has targeted 150,000 newborns in Victoria from 2021 to 2023, has already recruited successfully over 100,000 participants, infants and parents. This program has enabled us to collect and store 2 punches per baby, all of them as a link, and link these to different health and economic outcome measures. So a lot of data. These include physical and developmental milestones, parent-reported ePhenome and data linkage, mental health services, developmental outcomes and measures. ePhenome is an app that was developed that they all get reminders and they feel information is collected in different waves. And healthcare use and resource utilization for the first 3 years of life and into the future. We also have really productive stakeholder engagement strategy and a great group of stakeholders, not just Australian, but a lot of people from the States and Europe involved. And there's over 15 stakeholder organizations representing the condition screen. And as we increase the panel of condition screen, we suspect there'll be more stakeholders that will join the group. And we hold these meetings once every 6 months. So if anyone's interested, maybe worth having a discussion offline. Input provided into co-design materials for stakeholders and consumers to ensure inclusion of patient advocacy groups. This is our priority. And we're focused, so we have to coordinate all of this, a lot of people involved. So activities are implemented and led by Australian Genomics, Genetic Support Network of Victoria, and Rare Voices Australia. So this is a key rare disease organization in Australia. And here's a QR code where you can get more information about who is involved in US or Europe and Australia. Our 5-year goals are to have an accredited program established to mirror throughput and timing of standard care newborn screening. We want to enable assessment of what workforce, health, and patient support systems are required for program implementation. We are planning to use all of this information to put together an application to national policy framework. It's a little bit different to what it was a few years ago, but yeah, so there will be opportunity to add new conditions, if you have evidence, to consider addition of epigenes to newborn screening. And we will get clinically actionable screening threshold for conditions screened from obtained from population scale data, addressing the mosaicism issue. This will ensure early interventions for these disorders are uniformly available from birth. And we will get information on how we can expand Epigene's workflow to other conditions, and this will at little cost. So the significance is the program will lead to implementation of new model of genomic newborn screening, where parents and children would benefit from available treatments, so growth hormone for Prader-Willi and gene therapy for Angelman's, for example, when available. Diagnostic harms and costs will be minimized. This is particularly relevant to Fragile X, and especially in the light of reproductive options, because Fragile X is diagnosed on average at about 3 years of age, and some of the parents, or many of the parents, end up having multiple kids affected with before they know that the first one has it. So knowing that your first newborn has Fragile X has implications for seeking alternative reproductive options and having unaffected kids moving forward. And so the significance is also that we plan to perform comparisons of benefits of testing at birth to standard of care testing at later age to inform rational changes to policy and practice. We want to enable early trials of further novel interventions when this could occur to treat further and mitigate the conditions. You cannot perform a clinical trial if you don't have a cohort, and you can't have a cohort without having a newborn screening program. So it's a catch-22. And we're looking at establishing a pathways to expand the program for more conditions at little added cost. Future directions is to expand nationally, internationally. We have a wonderful collaboration with RTI. And so it's been quite productive, and sort of we're hoping that things keep on moving as they are in the States. Establish systems to manage and analyze data from different cohorts countries. Provide support to assist with grant application and further industry funding to allow technology transfer to other sites. Obviously, the more cohorts you screen, the more individuals and the more data you have for these rare conditions. And so if you have other suggestions, please email me. In terms of acknowledgements, I probably could have 6 slides like this, but these are the key ones. The key contributors are the families who participated in our studies, provided samples, and underwent assessments, 3 hours per family. Then key co-PIs in different universities and institutes throughout Australia, and key stakeholders outlined below, and major funders are Medical Research Future Fund, and HMRC, which is equivalent to NIH, Foundation for Prader-Willi Research USA, Victorian Department of Health, VMRAF, and Angelman Syndrome Foundation USA. So thank you to them. Without their support, we wouldn't have had data to get this program running. And so yeah, thank you for your attention. And here is a QR code and details if you want to go to our website to find out more. I guess I'm open for questions now. Amy.
Yeah, thank you so much, Dr. Godler, for that amazing overview of all your work. I'll start out with an easy question before we get into the technical details. Can you tell us how you guys are enrolling your 100 to 150,000 parents and children? At what stage? Is it before birth, at birth? How does that happen?
So my program, Epigenes is not actually enrolling them. They've been already enrolled and consented by GenV. And the details are included on the website, but they've got different strategies to do this through birthing hospitals. So the thing is, here in Victoria, we have a hearing program is very uniform, centralized, and it's in our hospital. And the person that's Melissa, who runs GenV, helped to establish it as well. So through there, we were able to consent, or GenV was able to consent, and through other sources, a lot of individuals to be part of this program. Does that answer your question? And the problem is, it's only, if you're doing something like this at that scale, you can only spend limited time with each individual. So you have to pick and choose what data you collect and how you consent.
Mm-hmm. What's the number of babies born in Australia every year?
The Australia, for the whole Australia, about 300,000 something, but in Victoria is 85,000. So our state, where we work, the pathology company, VCGS, test the whole state. So our lab, the BCGS lab, does the whole state, 85,000 a year.
Great. Thank you. Dr. Baker?
Okay, my turn. So I'm going to get technique. David, thank you. And I want to echo Amy, quite a comprehensive description. I think my question may be more detail on the technology and more is the clarification. And you mentioned that you bisulfur treat the DNA, then you do the concentration checking or not? I thought you said. I don't know because you have two sets. One is testing, development, and then you have applied to dry blood spots. My question is specific for dry blood spots because think about the newborn screening application. So after you do the DNA extraction, then you will do the bisulfur, and
We don't do DNA concentration. We do not measure DNA concentration. The DNA concentration is measured by the software. So you've got your bisulfite conversion, and we get concentration after bisulfite conversion from the software. So it's a lot better, and we're not just getting DNA concentration after conversion for everything. We're getting it for the amplicon that we're targeting, which is different in some cases to everywhere else. So that's the advantage, and that information is being fed by the software into the HRM data. I can tell you that high resolution melt is dependent on DNA concentration and its quality after bisulfite conversion, not before.
Okay, thank you. Another question I'm going to ask you is, I read your paper, I think a while back now, so if I don't remember, forgive me. Based on you looked at distribution, see the percentage in terms of methylation, and you can identify the Angelman wild type product, duplication and Prader-Willi. Tell me a little bit, just help me understand a little bit why you do second tier.
Why we do second tier?
Yeah, because you said the genome sequencing do second tier. If you do second tier, why not including the UBE3A so you can get the other one?
Okay, I can answer this. So right now, in terms of any standard of care newborn screening lab, they don't just do one punch and that's it. Even with biochemical tests, they do it on a second one to validate that they didn't mix things up. So you need to do another test on a second punch, doesn't matter what it is, before you actually go on to the family and ask for another sample. So the positive predictive value should be calculated from both punches as opposed to just single one. That's one aspect why we do second tier. The second one, why? So there are two questions there. Why we do methylation on another sample? The reason is we want to make sure that one, we haven't mixed anything up, so the results in methylation of normal result is coming from the right infant, and two, we have a parallel technique that users have completely different technologies that gives you the same result. We want to know that the methylation that we're picking up on one punch is real. That's why we do another methylation test on another one, on another punch. We can include UBE3A, but we can actually include it in genomics if we wanted to, but it would be missed if we don't do it for the first year. So remember, UBE3A is methylation not methylation sensitive.
Right. Yes.
Right?
Yes.
So we are, like, for X chromosome related conditions that we pick up, we have lysate that's left over, that we have a lot of it left over, where we actually have an assay that we run X and Y confirmation, so the sex is being confirmed. So theoretically, we could add another probe in there to go with to look at UBE3A, but we haven't done that.
Yeah. So I think I kind of probing my next question to you is that you mentioned that you use shotgun the genome sequencing right now. Do you have a plan use more long reads ones? And long reads ones. So this way you don't need a bisulfur treatment. You can directly identify, right? No?
It's not suitable for newborn blood spots. We've looked at this. We've done work on this. The actual definition of why it's not applicable is actually in the name. It's long read. newborn blood spots if fragmented. So if you've got fragmented DNA, long read is not applicable. It's wonderful technology if you've got good quality DNA, and this is something you would do if you collect another sample for confirmatory testing, but I would not apply. It doesn't work on blood spots, especially not a single punch. In terms of quantity.
You tried, right?
I can tell you it doesn't work. You can try.
I just take your word. But I think theoretically you described very logical, and I have the same concern because, like you said, if you start with a template, it's a fragmental how you get a non-reads to the end, right? I see your point, but I just wondering, is anybody have tried? And
yes, long read doesn't work on saliva either very well. So even on saliva stuff, it works really well from what I understand. Works really well on venous blood DNA, and you need quite a bit of it, but also the cost right now is quite significant too. So you would use it, you would potentially use it if it provides information beyond what you need to know. So if you're looking at phasing and doing other things that I can't get from short read, more fancy stuff, you would do it on 1 or 2, maybe 10 samples, but I won't do it on 100,000. You will blow out all your costs. So
thank you. I think I'm going to have a very quick, I let other people talk. You talk about the cost. So what the cost for you now to do a newborn skin giant spots, do a sequencing, do the process you have?
I can't tell you what the cost is. I can tell you it's the same as what, or very similar to what it costs to do SCID and SMA at the moment. And because the genomic...
Let me give you the number. SCID in a single-digit dollars. And then SMA, you multiplexing, basically, it's not, ignorable. So do you think they're comparable?
As I said, it's the same or very similar to SCID and SMA. So you have to keep in mind, we are running genomics on a second tier. So if you do 100,000, you would do genomic confirmation on 100 out of 100,000. If you divide it by a condition per infant, it ends up to be very low cost. And MSQMA and HRM, as you know, doesn't cost much. So, So yes, it's comparable to SCID and SMA, what is currently in standard of care. So cost is in line, material requirements are in line with what is currently being done.
Yeah, I just want a ballpark because, of course, the instrument and everything have to take a consideration.
It depends on your volume. I can't say the cost because it depends on how big the volume is. Obviously, the more you screen, the less the cost. So it's like how long is a piece of string?
Okay.
But it's not hundreds or thousands of dollars that you would get paid for in diagnostic settings.
Okay. Very quick last one. If I heard you correctly, the assay failure rate is 2%?
Well, for the conditional screen, yes.
Okay, thank you.
Less than 2%, less than 2%. It depends on the assay, but that you target, it varies between them. But yeah, less than 2%. But this is what you get for DMD and other things. So it's actually in line with what you would expect.
Thank you.
No problem. Thank you for questions.
Yeah, thanks, May. We really appreciate it. So, Dr. Godler, there's a question in the chat window, and I don't know if the person that asked that question wants to unmute themselves and have a conversation, or if you'd like me to read it if you're somewhere you can't unmute.
Yeah, hi, Dr. Brower. Yeah, it's fine. I was just kind of curious about, there was one graph you showed where the range of methylation on the S and RPN promoter between 25% and 75% was indicative of wild type. My question was, is there truly no differences in gene expression between a 25% methylated promoter versus 75% methylated promoter? Because it seems like 75% is kind of leaning towards being hypermethylated, as compared to promoter being only like 25% methylated as far as during via the PCR results. I was kind of curious about that range and how you came about those cutoffs.
Thanks for the question. So it wasn't methylated, it was methylation ratio. So let's not confuse methylation percentage with methylation ratio. So this is an output that the software provides. If you run high quality DNA, the actual range is between 50 and 60%. So it's a lot narrower. If you're using archival samples that are 6 years of age, the range becomes wider, and we discussed it in the paper, and it's between 25.25 and 0.75. It doesn't matter what the technical range is. What does matter is discrimination from your positives to get good positive predictive values in this setting. In terms of the expression of genes, within that locus, we've published on this, and there is variation in the neurotypical population, but it's not the methylation that necessarily drives that variation. So did I answer your question, or did I miss
Yeah, you
something?
did. Thank you.
Great. And Dr. O'Brien put a note in the chat window that in Australia, participation in newborn screening is not mandatory, but almost 100% of parents elect to uptake this screening. How come it's not mandatory? You want to talk a little bit about that, or?
No, the right person. You probably
No?
want some.
Maybe a question for your stakeholder group, huh?
I mean, the uptake is very high, and what I can say is, with GeneScan and the consortiums and us looking at using genomics for this purpose, we have to be very careful not to compromise the confidence of general public and affect the uptake. The same story is in the States, so that's why you have to do consented, tick all the boxes, and that's what we're doing. We do not want to compromise in any way what's happening right now in Australia with standard of care newborn screening.
You probably explained it in some of your earlier slides, but can you walk us through how you think your research fits into the overall, traditional newborn screening and genomic sequencing? So if you look 10 years down the road, what will we be doing with those dry blood spots?
Hopefully it's not 10 years, hopefully it's a few years from now, but so there's a lot of things happening in parallel. So genomics is revolutionary, it's changing everything. But with it, there are many issues that will take a long time to address. One major issue is when you do it, you get a lot of information. A lot of the information you don't want to have. The information that has insurance implications, the information that has implications for conditions, like onset conditions that ethically you don't want to be screening for in newborns. So there are ways, so people are working on ways to address this, and the cost is another thing. It's coming down, but it's not just the cost of the test, it's also the cost of storing all the information and using the information and security and various other things. So I think this thing is, what we're doing is complementary. The second tier is complementary to first year. I think it'll take a lot longer to get first year genomics into standard of care because of the issues that I've just mentioned. It does not prevent what we're doing to go in first. Also, what we're doing when we're looking at epi signatures and printing disorders and methylation changes, genomics is not going to pick it up as a first year. So I don't think that they're mutually exclusive, and I think what we're doing is actually going to provide information for the projects that are using genomics as first year as well, because they're doing a lot smaller numbers because of the cost than what we're doing.
One issue we've heard about in the United States is that, as new conditions are added to routine newborn screening, we're sort of running out of real estate on the newborn screening dry blood spot card. Are you guys running into that, or are you it seems like you can get samples pretty easily and that hasn't been a roadblock for you?
Well, it's a roadblock for everyone. That's why everyone is collecting the same, everywhere. Not Australia and US are quite consistent in terms of how much material is being collected. So a lot of material we use has been consented specifically for the identified research. What we are doing is only 2 punches. We had to, if you want to run a program like this, it needs to work on a single punch and the second one for confirmation. You will be struggling getting more materials from newborn screening labs because they need to keep things for backup. So we can screen a lot more from the materials that we have than the panel that's in this presentation. That's why I said we're expanding the panel of conditions that we're screening, just to get more value for buck. So we've established all of these. Might as well do it for other conditions as well that we can pick up. But this is the issue that everyone is going to face as they decide to add more condition. And with genomics, a lot of the genomics technologies they use a lot more than a single punch to be able to get comprehensive, especially if it's not PCR based. You need probably 10 punches. So it's even more of an issue than what we faced. you might need to have a parallel system running where you collect additional materials just for the research study.
Thank you. Any additional questions for Dr. Godler? I'm sure you put your email and all the QR codes throughout your presentation. Your talk will be on our website shortly. And I just want to remind everybody that Dr. Chan and I are editing a special issue of the International Journal of Neonatal Screening. So Dr. Godler and others, if you want to submit your work, we would love to have you. This is just the theme of the special issue, which really goes from start to finish in newborn screening and hopefully include some parent perspective and papers from advocates. Just a reminder that we'll continue to host these monthly pilot webinars until February. And here's a preview of the upcoming webinars. So in December 7th, we'll hear reports from the IDIQ newborn screening pilots in the United States. In January, we have a special guest, Dr. Carrie Harding, who will talk about phenylketonuria, insights into pathophysiology and novel treatments. And then to round out our monthly pilot in February, we'll have a round robin from several leaders across the nation who are looking at newborn screening for new conditions. So we'll hear from Dr. Richard Parad, Nikki Armstrong, and Holly PA. Note the change to the February time due to the advisory committee meeting. It's not a change in the day, it's a change in the week because the week prior, that Federal Advisory Committee is meeting. So again, thank you everyone for joining today. And thank you again, Dr. Godler, for sharing your amazing work. I'm sure we'll all be in touch and looking forward to your new publications as they come out. So best of luck.
Thank you for the opportunity. I appreciate it. All the best.
Thank you. Have a great afternoon, everybody.